At AS level, you treated gravity as a constant downward pull. That works perfectly for dropping an apple in a classroom. But the moment you launch a satellite or map a comet's trajectory, that approximation shatters. In this unit, we zoom out. You will learn how gravity actually behaves across the vacuum of space, weakening as distances grow. Crucially, mastering the mathematics of gravity here will effectively teach you half of the electromagnetism course in advance, because the field architectures are identical. We begin by defining exactly what a field is. Gravitational field strength, little g, is the force exerted per unit mass on a small test mass. You will move from sketching uniform, parallel field lines near the surface of the Earth to drawing radial field lines that spread out into space. This is your toolkit for mapping the invisible pull of planets. Next, we quantify that pull. Newton's law of gravitation is the mathematical rule governing the attraction between any two masses in the universe. You will see how the gravitational constant, big G, scales the product of two masses, and how the force drops off with the square of the distance between them. This single equation is the starting point for almost every paper 4 mechanics question. By combining our first two ideas, we derive the field strength of a point mass. You will learn to calculate exactly how a planet's gravity weakens as you travel further away. Notice this signature inverse square curve. We will also look inside a uniform sphere, exploring why gravity drops to 0 at the center of the Earth. Mastering these profiles is essential for exam calculation questions. Then we shift our focus from forces to energy. Gravitational potential is the work done per unit mass to bring a test mass from infinity to a point. Because gravity is strictly attractive, this value is always negative, only reaching 0 at an infinite distance. This energy framework is your primary tool for solving complex launch scenarios and calculating the exact velocity needed to escape a planet entirely. Finally, we put these masses into motion. Orbits are simply circular motion where gravity provides the invisible string, the centripetal force. You will equate gravitational force to centripetal force to derive orbital speeds and prove Kepler's third law. We will also evaluate the precise altitude required for geostationary communications satellites, a heavy-hitting topic that Cambridge examiners love to test. By the end of this unit, you will be able to map radial fields, calculate the forces between distant planets, analyze the negative energy wells they create, and derive the mechanics of orbiting satellites. You are building the mathematical architecture of the cosmos. Let us begin.